Thanks for coming back, you guys. And this is an important piece of our little lecture series. It's the ozone layer. This is the good up high part, not the bad nearby. And when I say up high, we're talking about the stratosphere, right? Not the troposphere. This is where you got all that photochemical smog. And so one thing I want to talk about just for a moment is just to remind you guys that the sun is putting out the whole range of electromagnetic radiation. Most of it's visible light, but if you see just a little bit shorter wavelength, you've got ultraviolet radiation. I think most of us know what that is because this is why you're putting sunscreen on. To protect yourself from that UV radiation. Or when you get sunglasses and there's that little sticker that says UV radiation, that's what we're talking about. But the thing that protects us the best from that is the ozone layer. And here you can see just like the levels of ozone as you start from sea level. And here's our photochemical smog in the troposphere. But then up here in the stratosphere is where you've got a huge amount of ozone. And we like that. That's the good up high part. What happens, and I don't love this diagram, but it gives you the idea. So the ultraviolet radiation comes in and it will break apart the O3 molecule or an O2 molecule. But the idea is that energy is going into breaking apart the molecule rather than coming down to basically where we are in the troposphere. And so with this one, you can see it broke apart an O2 molecule, which releases an oxygen, which then can combine with O2 to make O3. This could also be an O3 molecule that the sunlight is breaking apart. And so you get a nice balance there of O3. This is natural O3 destruction, right? And then it just reforms. And so it's just like it's an equilibrium reaction. It keeps going back and forth, right? But so the problem is back in the 80s, scientists came up with what they thought was like the miracle molecule. It's called the chlorofluorocarbon. Say it once. Chlorofluorocarbon rolls right off the tongue, or CFC. Here's our CFC, and I would write this down. And so what it was used for was it's like a gas that didn't react with anything in the troposphere. So they thought you could do anything with it, and it wasn't going to cause any problems. It was inert, so they thought. And so they would use it as a gas propellant. And so if like an aerosol can, like spray paint or hairspray, picture big hair, 80s hairspray, and you'd spray it and all the gas would go out and the CFCs would eventually go up into the stratosphere where you've got the destructive part of it. They also used it for styrofoam. Foam came out in the 80s, and so just picture going to McDonald's, everybody did it. You get your Big Mac and it came in a styrofoam container, you open it up, Big Mac on one side, French fries on the other side. It was like the best. Nobody knew any better. Now they don't have that anymore. But the biggest use was, well, they also used it for cleaning motherboards for computer parts and stuff, blasting that gas in there to get all the dust out and stuff. But the biggest use was as a coolant for refrigerators. And this is the one you want to remember: refrigerators, air conditioners, because it's cold. And so it would be they'd call it Freon, but it's CFCs. And it would basically make your refrigerator stay cold, or if your air conditioning in the car was leaking and it wasn't working, they just fill it back up with Freon or the CFCs and it would continue to leak. Or those refrigerators would hit the landfill and break just like the styrofoam, and then the gas gets released. Nobody thought it was any big deal until they figured out that it was actually it was reactive and it was happening up in the stratosphere. And so it's just like how ozone is naturally broken apart by ultraviolet radiation. The chlorine off of chlorofluorocarbon gets knocked out by radiation, and that chlorine is really reactive. Like all those halogens in the periodic table, that column, chlorine, fluorine, bromine, I think too, will be really reactive. So the chlorine atom, follow this picture. I pulled this from your textbook. Chlorine reacts with O3, knocks out the two oxygens there as an oxygen molecule. Now you got chlorine monoxide, and it just delivers that oxygen to another lone oxygen, and it makes O2. And it releases the chlorine to do the cycle again. So the chlorine keeps attacking O3s along with the sunlight. And so basically you're throwing off that balance. And the problem is, so this is a catalyst. It's not used up, and it can be active for a very long time. They think up to 100 to 150 years It can break down, one chlorine atom can break down up to 150 or 100,000 molecules of ozone. And so it's pretty destructive. And so they figured that out, which is good because then we can do something about it. But one of the things I wanted to point out, though, is when they figured it out, they did it in the South Pole. And so here's a picture of, you can see the blue is the hole or the thinning ozone layer. So 79, 87, 2006, you can see that there is a thinning of the hole. And so this isn't like a donut hole you can stick your finger in. This is just thinner ozone. And a good question is, why is the hole bigger in September and October, November in the southern hemisphere? And so you got to remember, southern hemisphere's got the opposite seasons as we do. So September through November is spring down there. In the wintertime, which is like our summer down there, it is super cold, colder than we can imagine, and it's dark. There's no sunlight. It's like, you know, the land of the midnight sun down there too. And so it's dark, it's cold, and what they think is that up in the stratosphere, you're getting polar ice clouds that are just building, and they contain all these CFCs in there, and they get concentrated. And then when spring does hit, all of a sudden now you've got sunlight. It starts to warm up a little bit. These clouds release all this chlorine, and now you've got the sunlight breaking apart the ozone molecules down there too. And so all of a sudden it happens at once, and you get a really pronounced hole. And then it gets really warm, and pretty soon it just starts to all dissipate, right? And so it's a thinner ozone layer everywhere, but it starts down here, and it does it a little bit in the Arctic, in the North Pole as well, but it's more pronounced in the South Pole. So that's what it looks like. People get confused between climate change and ozone layer, and so I would recommend jotting this down. I got a little chart here. It's not Cornell, but just to break it down, we got the hole in the ozone layer. These are happening in different places. So that's in the stratosphere, versus climate change is all in the troposphere. That's where we're experiencing that. Radiation, UV light versus light and infrared radiation. So they're different. Causes, totally different. We got the CFCs we just talked about, and then we've got all these greenhouse gases. CFC technically can be a greenhouse gas. It has more than 2 atoms, but it just goes up to the stratosphere. The mechanism for how this works, totally different. We got what we just went over with the UV radiation and the chlorine atoms and ozone destruction versus the greenhouse effect. The effects are different too. Here we got skin problems with sunburns and eye cataracts, not just for people, animals too. You can also burn plant material too. So the plant tissue gets burned and it can't do photosynthesis as well. Versus for climate change, and we've gone over this, but you got a whole different slew of problems that are different. Finally, to leave you with something positive, the Kyoto Protocol was the big one for climate change. It was pretty much a failure. The Paris talks happened in 2015, and that was a little bit more positive, but no binding agreements or anything like that. With the Montreal Protocol in 1987, that's in Canada, there were binding agreements, and so the world came together, or some of the power nations that were involved with making these CFCs and industrializing them, and they agreed we're not going to do it anymore because it's destructive. And then they found substitutes, and a whole market built up around that. And so it's two different issues. I think climate change is a little bit more difficult because it's related to our favorite type of energy, but it does give us hope that these things can happen. And so anyway, there it is, the good, the bad, the ugly, good up high, bad nearby. Thanks for sticking with me.